the most expensive warship ever built, cannot fly its most advanced fighter jet. Let that sit for a moment. The USS Gerald R. Ford, CVN-78, a ship that cost $13 billion to construct, that represents the most technologically advanced aircraft carrier ever put to sea, that carries the most sophisticated electromagnetic launch system in naval history, is currently operating in the Middle East, supporting Operation Epic Fury, without a single F-35C Lightning II in its air wing. The jet that was supposed to define the future of carrier aviation, the fifth-generation stealth fighter that the Ford was specifically engineered to support, is not aboard. Instead, the most capable carrier ever built is flying F/A, 18E/F, Super Hornets, fourth-generation jets, aircraft whose basic design dates to the 1970s, the same aircraft that every other carrier in the fleet has been flying for decades. The Abraham Lincoln, a Nimitz-class carrier commissioned in 1989, older than many of the sailors who crew it, is flying F-35Cs right now in the same theater. A 35-year-old ship is doing something that the Navy's most modern and most expensive carrier cannot do. How did this happen? How does a ship designed from the keel up to operate fifth-generation aircraft end up being the only carrier in the fleet that cannot do it? And what does this saga of engineering ambition, congressional pressure, budget decisions, and cascading technical problems tell us about the real challenges of building the next generation of naval power? This is the story of the USS Gerald R. Ford and the F-35C. It is a story about what happens when you try to introduce too many new technologies simultaneously. About the gap between what looks good in a program brief and what works reliably on a flight deck in combat conditions. And about the strategic consequences of a $13 billion ship that cannot yet fly the jet it was built for. The Ford was designed to be revolutionary, not evolutionary, revolutionary. Every major aircraft carrier before it had been built around the same core concept established by the Midway and Forrestal classes in the 1950s and refined through the Nimitz class, which entered service in 1975. Steam catapults, arresting wires attached to hydraulic systems, a nuclear power plant, an angled flight deck, an island superstructure. The basic architecture had not changed fundamentally in 70 years. It worked. It was reliable. Sailors understood it. Maintenance was understood. The whole system had been refined through decades of operational experience into something that was genuinely dependable under combat conditions. The Ford threw most of that reliability history away and replaced it with systems that had never been operated at sea. The Electromagnetic Aircraft Launch System, or EMALS, replaced the steam catapults. Instead of using steam pressure accumulated from the ship's nuclear reactors to accelerate a shuttle down a track and launch aircraft, EMALS uses a series of linear induction motors driven by a sophisticated energy storage and power conversion system to generate the acceleration force electromagnetically. The theoretical advantages are significant. EMALS can apply launch energy more precisely than steam, reducing airframe stress on launched aircraft. It can handle a wider range of aircraft weights, from heavy strike fighters to light unmanned systems, without mechanical adjustment. It generates fewer maintenance hours per launch than steam catapults over its theoretical life cycle. And it produces no steam, which means no steam-related maintenance, no steam burns to sailors, and no need for the complex infrastructure of high-pressure steam management that the Nimitz class requires. The Advanced Arresting Gear, or AAG, replaced the hydraulic arresting wire systems. Again, the theoretical advantages are real. Greater energy absorption capacity, smoother deceleration profiles that are gentler on airframes, the ability to handle a wider range of aircraft recovery weights. Everything about EMALS and AAG on paper represented genuine progress over what they replaced. But paper and sea are different environments, and what emerged as the Ford entered testing and then operational service was a picture of systems that worked when conditions were ideal, and failed at rates that were unacceptable for a combat vessel when conditions were anything less than ideal. The fundamental problem with EMALS was reliability. The system's energy storage and power conversion subsystems were interconnected in a way that made them difficult to isolate when a failure occurred. When EMALS had a problem, the investigation and repair process required halting flight operations entirely because maintenance could not be performed on below-deck components while the system was active. For a steam catapult, individual components could often be isolated and worked on while the other catapults continued to function. EMALS did not offer that kind of redundancy in its original configuration. A single failure could halt sortie generation for the entire ship while the problem was located and resolved. The Department of Defense's Operational Test and Evaluation Office, the independent body responsible for assessing whether new military systems actually work as claimed, issued assessments of the Ford that were extraordinarily blunt for official government reports. The EMALS and AAG systems remained unreliable and broke down too often. Problems with reliability and maintainability continued to adversely affect sortie generation and flight operations. The reliability of those systems had not appreciably changed from prior years despite ongoing development work. The ship relied on off-ship technical support to address problems it could not fix with its own crew and equipment. Then President Trump, never known for diplomatic language when discussing programs he found frustrating, described EMALS in an interview with Time magazine as requiring someone to be Albert Einstein to really work it properly. He wanted to go back to goddamn steam. Whether that characterization was technically accurate or not, it reflected a genuine frustration within the Navy and Congress about a system that had cost billions of dollars more than projected and was still not performing reliably years after the ship entered service. The AAG faced its own separate problems. During early operational periods, the system experienced failure rates well above acceptable thresholds for cycles between operational failures. Replacement parts were difficult to obtain. The ship had to rely on off-ship technical support for repairs that should have been within the capability of the shipboard maintenance team. And the Navy discovered after the fact that a cost-saving decision made during construction, the elimination of a fourth AAG engine that had been part of the original design, had removed a redundancy capability that turned out to be operationally important. The fourth engine would have improved reliability, improved pilot boarding rates, and restored the ability to rig an emergency barricade in the event of an engine failure. It had been removed as a cost savings measure. The cost savings turned out to be false economy. The cumulative effect of these reliability problems was a deployment readiness picture that was significantly below what the program had promised. The Ford took delivery in May 2017. Its original projected deployment date was 2018. That date slipped, then slipped again. Pushed back ultimately as far as 2024 according to some estimates, 6 years behind the original schedule. The $13 billion ship that was supposed to be in the fleet and generating combat power was instead sitting in port or in limited operational status, accruing maintenance costs and delaying the capability insertion it had been built to provide. But the EMALS and AAG reliability problems, as significant as they were, are actually not the primary reason the Ford cannot deploy F-35Cs. That distinction belongs to a separate set of infrastructure requirements that the F-35C needs before it can operate from a carrier in sustained combat deployment. An F-35C is not simply a more capable aircraft. It is a different kind of aircraft entirely in terms of the support infrastructure it requires. The F-35's stealth coatings require specialized maintenance facilities, including climate-controlled hangars, where the low observable surface treatments can be applied and repaired without contamination. The aircraft's sophisticated avionics systems require a dedicated maintenance infrastructure that does not exist on the Ford in its current configuration. The Autonomic Logistics Information System, the software framework that the F-35 uses for maintenance tracking and diagnostic support, requires specific hardware and network infrastructure aboard the ship. The Aircraft Intermediate Maintenance Department, the shipboard organization responsible for maintaining aircraft systems beyond the capability of the squadron's own mechanics, needs to be equipped with specialized test benches and tooling specific to the F-35C's unique systems. And the weapons handling and storage infrastructure for the F-35C's internal weapons bay configuration requires modifications to the ship's ordnance handling systems. None of this was included in the Ford's original construction. The decision to defer F-35C compatibility infrastructure was made years before the ship was completed, driven by cost pressures and the assumption that the modifications could be made later during scheduled maintenance periods. The consequence of that decision is a ship that was delivered to the fleet in 2017 that has been the subject of congressional attention, GAO reports, and operational testing assessments for nearly a decade since, and that as of the beginning of Operation Epic Fury in February 2026, still cannot deploy the F-35C in operational service. The irony that makes this story particularly sharp is the contrast with the Abraham Lincoln. The Lincoln is a Nimitz-class carrier commissioned in 1989. It uses steam catapults. It uses hydraulic arresting gear, systems that Trump called goddamn steam and that the Ford was designed to replace. The Lincoln underwent its modifications to support F-35C operations and deployed with F-35Cs for the first time in late 2022. A ship built 35 years ago using technology that the Ford was supposed to make obsolete is doing in the Arabian Sea right now what the Ford cannot. The F-35C's flying combat missions over Iran are launching from the Lincoln's steam catapults, not from the Ford's revolutionary electromagnetic ones. This is not to say that EMALS is a failed technology or that the Ford class is a failed program. The larger picture is more complicated than that narrative. By 2025, operational assessments began to indicate that EMALS reliability had improved significantly from the early years. The systems that had been described as unreliable and breaking down too often were performing at higher levels of availability as the crew's familiarity with the system deepened and as software and hardware improvements were implemented. The Ford has conducted sustained combat operations in the Middle East since being deployed with Operation Epic Fury, operating in a high-tempo environment that is the ultimate test of a warship's systems. Its air wing has launched thousands of sorties. Its EMALS has been operating under real combat conditions. And the reports from the field do not describe the catastrophic reliability failures that characterize the ship's early operational history. The USS John F. Kennedy, CVN-79, the second ship in the Ford class, is being built to the F-35C compatibility standard from the beginning of construction. The infrastructure requirements that were deferred on the Ford are being incorporated into the Kennedy as part of the original design. The Kennedy will commission with the ability to operate F-35Cs without the retrofit modifications that are now required for the Ford. The other Ford-class carriers planned in the program, CVN-80, Enterprise and CVN-81 Doris Miller, will follow the same approach. The Ford is the outlier, the first of class ship that bore the burden of introducing too many new technologies simultaneously, and is now paying the price of that ambition in capability gaps that take years and significant resources to close. But the Ford is the ship that is in the theater right now, and the question of what it means strategically to have the Navy's most expensive and most technologically advanced carrier operating without its most capable aircraft in an active combat environment is not a trivial one. In a conflict against Iran, the absence of F-35Cs from the Ford's air wing is a real but manageable limitation. The F/A-18E/F Super Hornet is a capable fourth-generation fighter, and in the degraded Iranian air defense environment created by the opening cyber and electronic warfare operations of Epic Fury, its lack of fifth-generation stealth is not a critical vulnerability. The mission sets that the Super Hornet is executing over Iran, striking fixed targets in a suppressed air defense environment, providing close air support, performing interdiction missions against known military facilities, are missions the Super Hornet does well. The F-35C's specific advantages, primarily its ability to operate in a denied environment where Iranian air defenses are fully active and integrated, have been less critical in this conflict because those air defenses were degraded before the air wing arrived over target. Against a more sophisticated adversary, or in a scenario where the air defense suppression phase had been less successful, the absence of F-35Cs from the Ford's air wing would matter much more. In a Taiwan contingency, for example, where Chinese integrated air defense systems are genuinely formidable, and where the ability to operate in stealth is potentially decisive, having the carrier strike group's flagship unable to fly the jet specifically designed for that threat environment would be a significant capability shortfall. The deeper strategic lesson of the Ford and the F-35C is about program management and the risks of revolutionary versus evolutionary development. Every major capability that the Ford introduced, EMALS, AAG, the new nuclear reactor design, the new island configuration, the new weapons elevators, was individually justifiable on technical grounds. Each system offered real advantages over what it replaced, but introducing all of them simultaneously in a single platform, with the accompanying uncertainty about how they would interact with each other and with the operational environment of a working carrier, created a complexity and a testing burden that the program was not resourced to handle effectively. The result was a ship that entered service years late, billions over budget, with systems that were not reliable enough for the operational demands placed on them, and without the infrastructure to operate the aircraft it was designed to fly. The Navy has learned from this. The Kennedy incorporates the lessons of the Ford, integrating F-35C support infrastructure from the start and benefiting from the hard-won reliability improvements that came from years of operating the Ford's EMALS and AAG under real conditions. The Ford itself is undergoing modifications that will eventually bring it to full F-35C compatibility. The program is not broken beyond recovery, but the cost of the lessons learned, measured in dollars, in years, and in the capability gap visible every day that the Ford operates in combat without the jet it was built for, has been substantial. The world's most expensive warship is at sea, under fire, right now. It is doing the job it was sent to do. Its air wing is effective. Its EMALS is working. Its sailors and aviators are performing with the skill and dedication that the United States Navy demands of its people. But the F-35Cs are on the Abraham Lincoln, and that is a fact that $13 billion and nearly a decade of operational service have not yet changed. If you want to understand the full picture of U.S. carrier aviation capability, how the Ford-class program is evolving, and what the integration of fifth-generation aircraft onto American carriers means for the future of naval air power, subscribe to Navy Power Decoded. Every video goes deeper than the surface. Every analysis is built on the facts that matter. The Ford is the future of American sea power. Just not all of it. Not yet. There is one more dimension to this story that deserves attention, because it connects the Ford's F-35C gap directly to the broader competitive picture the United States faces in naval aviation. In September 2025, China achieved something that made headlines in every professional military publication on Earth. The People's Liberation Army Navy's carrier Fujian, China's most advanced aircraft carrier, successfully launched a Shenyang J-35 stealth fighter using its own electromagnetic launch system, an EMALS equivalent Chinese system on a Chinese carrier, launching a fifth-generation stealth fighter. It was the first time in history that a stealth jet had been launched from a carrier using electromagnetic catapult technology. The first time in history, not by the United States Navy, by China. The USS Gerald R. Ford has been at sea since 2017. It has EMALS. It has been conducting launch and recovery operations for years. F-35C test aircraft from the Air Test and Evaluation Squadron VX-23 successfully launched from the Ford using EMALS during developmental testing in 2022, validating that the aircraft and the launch system are fundamentally compatible. But those were test events, not operational deployments. No F-35C squadron has ever deployed operationally aboard the Ford. China's Fujian launched a J-35 operationally from its electromagnetic catapult system, before the United States Navy ever deployed an F-35C from the world's first ship equipped with that technology. This is not a crisis. The United States Navy's overall carrier aviation capability remains the most formidable in the world, by every meaningful measure. The F-35C is operationally deployed on multiple Nimitz-class carriers, including the Abraham Lincoln, which is demonstrating the jet's combat capabilities right now over Iran. American carrier pilots have more hours in fifth-generation aircraft than any other naval aviation force on Earth. The gap between American and Chinese carrier capability, measured in experience, training, logistics, and overall systems integration, remains very wide. But the symbolic dimension of China's achievement matters because symbols in military competition carry strategic weight. The message Beijing chose to send in September 2025, that China had mastered electromagnetic carrier launch technology before the United States had deployed a stealth fighter from the ship that technology was built for, was a deliberate communication to regional audiences, to American allies, and to the U.S. Navy itself about the direction of the naval competition. The Ford's program managers, the Navy's acquisition leadership, and the Congress that funds carrier programs will all be studying that September 2025 Chinese launch with attention and some discomfort. Because the story of the Ford and the F-35C is ultimately not just a story about technical problems and deferred infrastructure. It is a story about what happens when a program cannot deliver the capability it promised on the schedule it promised, in a competitive environment where adversaries are not waiting for American schedules to be met. The Ford will eventually fly F-35Cs. The modifications are underway. The Kennedy will deploy with them from the beginning. The program will reach its intended capability. But the years that gap has existed, and the fact that it still exists while the Ford operates in combat, are reminders that revolutionary ambition and program execution are two different things, and that the distance between them is measured in time, money, and capability that adversaries use to close the gap. $13 billion, the most advanced carrier ever built, and the most capable jet in the air wing is still on the other ship.